Hello, this is Philip Myers of PEMY Consulting. Welcome to Unit 3, Engineering Unit Standards and Systems. One of the first engineering standards was the Royal Egyptian Cubit. It's basically a granite yardstick. Did the standardization of length work? Well, they say that the pyramids are accurate to 0.05%. I can guarantee you that with the best modern tape measure that you could get, you wouldn't be able to do this accurately measuring the dimensions of your house. In 1889, the international prototype of the kilogram, called the IPK, here it is right here, was used to define the magnitude of the kilogram until just recently in 2019. In Gaithersburg, Maryland, 40 feet underground, NIST stores a replica of the IPK standard for the mass, which is made of a platinum iridium alloy. You need 3 different keys and 3 different people to unlock the room for you. The security is impressive. The alloy is about twice as dense as lead and is a small cylinder that's kept in the vacuum-packed jar. In spite of best efforts, the various handful of these replicate weights used throughout the world to calibrate weigh balances all vary somewhat, and they are not stable with time when it comes to super high accuracy. All the causes are not known, but a few is that molecules of mercury vapor from the air are picked up and absorbed by these weights. Handling, of course, causes some rubbing off of atoms of this alloy, and even absorption of gases from the air affect the weight. So the weight is not stable. The total variation has been about 50 micrograms change in weight over the last decades of use. That's about the weight of an eyelash. As of May 2019, the IPK mass is no longer the standard. The standard is now based on Planck's constant, which is a physical constant of nature. The machine you're looking at is the Kibble balance. It's used to make the relationship between Planck constant and the standard kilogram. If you want to know more about this link is very good. So we next need to talk about the difference between dimensions and units. Dimensions are stuff, things, quantities that you can measure. The units are the agreed upon way to communicate how much of that stuff there is. So for example, a spilled barrel of oil, I might want to know the thickness, the length, the width, the volume. Those are examples of dimensions. To express it, I have to use units. These are arbitrary, agreed upon measures, like the kilogram or the foot. You can see that the English units are very odd. They're different barrels, gallons, teaspoons. An example of another prototype for the meter was this bar that was made in 1889. It's been used up until 1960, when they changed the meter to be defined by the speed of light, the number of wavelengths in some given frequency of light, which is much more accurate and stable with time. Also, we need to understand primary and secondary units. Primary are the building block. They're also called fundamental. So, for example, F equals ma. The mass is a primary unit, but acceleration is a derived or secondary unit because it's made of length divided by time squared. You'll often see MLT, which means mass, length, time systems. And then there's FLT for force, length, and time. MLT is the SI system basis. They use mass, length, and time. The U.S. engineering system and British gravitational use FLT. We'll talk more about that in a minute. Now, 1 Newton is a force required to accelerate a kilogram to an acceleration of 1 meter per second squared. Here's a little exercise for you. I started it by putting in the dimensions here, writing down the applicable equations and units, and the same thing for mass. You can go through this diagram and do the same. It's very good for understanding. Again, we're going to review Newton's law, F equals ma. This is net forces that we talked about earlier. The arrows indicate that these are vectors. You have to worry about direction when you're in 2 or more dimensions, but for purposes of this, we can drop the references to direction. 1 pound force is 1 slug foot per second squared. 1 pound of force is also 32.2 pounds mass foot per second squared. Note that the slug is 32 times larger than the pound mass, and that's because this is a coherent system. The Newton, of course, also a coherent system of units, is 1 kilogram meter per second squared. There's 7 primary dimensions that make up all units used in nature or by people. Mass, length, time, temperature, luminous intensity, electric current, and the amount of a substance. Here are the names. Here are the units. This is in the SI system. And again, now we know why force and pressure are not shown. They are derived. This table is one that I have not seen before and was developed for this course. People talk about 3 different kinds of systems, the absolute and gravitational. They sometimes mention engineering systems. For us, this is going to mean the USCS system. The bullets are fundamental units, so force is derived in the absolute system. The absolute system is called absolute because it works anywhere in the universe without reference to a standardized gravity. Gravitational, of course, is using a standardized gravitational constant. If you use a slug, it's a coherent system, but we use the pound mass. We've made the pound mass equal to the pound force, so both of these can be considered derived or base units. I wonder about the type of person who came up with a slug as the name for the mass. Perhaps a slug unit would be in common use today if the gross slug name was not being used. As we mentioned, the slug is bigger than the pound and also, of course, the kilogram. Its mass is 32.2 pounds and it weighs 32.2 pounds force. The poundal is another rational coherent system, and it is the acceleration, it is the mass where if you put 1 poundal of force, it would accelerate at 1 foot per second squared. So it's 1/32 the force of a pound force. And this, of course, would also be a good system to use, but both systems are not common and I think are falling out of use. Of course, the system we use is a pound force, 32.2 pounds mass feet per second squared. You must carry this 32.2 in all calculations when using the USCS system of units. Another precaution of using standards is standard conditions. When working with gases, the famous equation PV equals nRT, pressure and volume, you have to agree on a system of standard conditions. So here's an example that shows 3 different systems, SPE, OSHA, SCA, QMD. Here's Imperial and here's a DOT system. Each one, even though they have the same temperature, 60 degrees F, uses a slightly different pressure for atmospheric pressure. So you have to be careful that you pick a system, stick with it, and then document it and make sure everyone knows that your calculations are based on that system. Here's like a reference to API 2000 that's talking about tank venting, which you need to be working with standard conditions. And they say that it's 60 degrees Fahrenheit, and they precaution that it's not the same as normal conditions. Normal conditions is not a standardized term, so you'd have to read the standard to see exactly what they're referring to. The point is that industry standards use standard conditions. What did you learn? We learned about dimension versus unit, fundamental versus derived units, physical object or physical constant. All 7 base units in the SI system are now based on physical constants and no longer on comparison to physical objects. That makes the system much more stable and accurate over the course of the next years. Types of systems used: the absolute gravitational and engineering USCS, standard conditions, and that industry standards use standard conditions, and you must know what standard conditions you're working with. Thank you, and we'll see you next time.